Hey, what's up, guys? So here we are back again at the HVC Optimal Start Math Playground, studying mechanical engineering theory for how to optimally start HVAC systems. Based off of research, we're feeding in data from the building and looking at some math models defined by the white paper by PNNL, and then we're in a variety of different ways calculating how many minutes it takes to warm up and cool down based on a couple of these models. And we're up to here. We're still looking into the some of the code that's running behind the scenes for matrix multiplication and some of manually doing some of the math. Before we whizzed through this with using some of the math libraries in Python, but here on the Vibe Coder repo, I have this actually running in the field right now. So this is the Niagara framework, which has been kind of nice for testing this stuff out. We have all four models defined by PNNL, except we're doing the linear regression, multiple linear regression, all manual, doing all the matrix multiplication ourselves, because in Java world there is no math libraries. And this block, which I'm still actually testing out in the field, over time it'll use which model has the best average squared error. So yeah, we'll just maybe look into this little by little. There's a ton of parameters and lots of code in Java that's that's running in the field. So it's still a work in progress, and I'm glad that I've started this trek of doing some of the math by hand, because I wasn't going to include models 3, 4, and 5, or I'm sorry, 3 and 4, because of this. So this is actually an old screenshot. I have to upgrade this screenshot, but we do actually have 0, 1, 2, 3, and 4, which I think I showed yesterday. So here we are. Let's jump into it. So I've been saying read the paper if you haven't read the paper. We've looked at it a little bit. So this is what PNNL did this research, the resistive capacitance model. Like we said, we're still doing model 3, so running the linear regression manually. So let's get into it. I think we're on bonus day 4, which I have a little bit to learn here. So okay, so let's do it. So let's solving linear systems, Gaussian eliminations. Excuse me. So goal is to solve without math libraries. So the concept and definitions: model 3 solves x transpose x beta, I guess, x transpose times y. The Gaussian elimination removes variables step by step until the system can be solved. Steps: eliminate variables row by row, back substitute to compute coefficients. Gaussian elimination is stable in protocol across all languages. So this doesn't make a lot of sense to me, but I suppose I can just start putting it in our little math lesson script. And I'm just going to say, as ChatGPT, day 4, bonus, Gaussian lesson, how to do, see what it says here. So you giving AI a bunch of context, what you're doing, and it should be able to assist. It's also interesting, there's actually quite a bit that, since I've been using AI a lot, at least ChatGPT I use the most. A lot of people are using Claude, you name it. Everyone seems to have like their favorite tool. I do like Gemini 3. I will admit I use that quite a bit too. But ChatGPT has kind of been my go-to. So it even somehow it has like a lot of saved memory about me, like even on blank chats, like it seems to know quite a bit about my background, which is kind of interesting how they do that, because I know like the models only have a certain amount of context, so it's kind of a mystery to me how it knows. So okay, so this is here's how we flesh out day 4, section min example, section 5 micro example. So we're solving ax equals b, where x equals that transposed. So write an augmented matrix. That's what that is. Interesting. So if we did that, I guess. Seems like this should be 2, 3. Forward eliminated, make it upper triangular. Eliminate the x term in row 2. Looks like they're just doing like a lot of division and minus. So how we could do this all by hand. Solve by hand. Seems like a neat exercise. Yeah, I'm gonna say pure Python. All right, so it's coming up with a little function here. Here's our matrix, matrice. So, wow, and it's going through quite a bit of some computer science magic here. Back substitution. This is really interesting. So, like I was saying before, like we could have like a whole college semester on this alone. I personally don't have the time to completely crank all this out, but it's really neat though. At a high level, like I understand, what is going on. It's building, like we were slicing the arrays earlier, and then it's doing the math by whatever slice, you're trying to get from there. Back substitution. A little bit of division, multiplication, so yeah, really neat. And that's how they did it by hand. Minus 0.5, negative 0.5, 0.5, and 3/2. Maybe I will try this by hand by paper. It would be a really good exercise for it to sink in. But yeah, pretty cool. Okay, so we got, what happens if a pivot is 0? I think you'd be divising by 0. You would be divising by 0, us exactly. Don't want to divide by 0. Looks pretty cool. Add this line before dividing. So that's just saying if you accidentally do that, break out of our program before it crashes. Why is this preferred over determinants? Let's see what ChatGPT says about this one. You've crossed into real linear algebra moment. Gaussian eliminates scales, determinants don't. Determinants are mathematically elegant, but computational awful. That's Cramer's rule. Clean, closed form, symbolic, cost of computing determinant, using the cofactor expansion, and times n determinant costs. So this is getting into computer science terminology on computation theory, on O to the nth. This is where computer science scientists study on complexity, O to the nth log complexity or whatever. Determinants are throwaway information you actually need, so interesting. So HVAC controls analogy. Determinant. See, this is how ChatGPT knows me. Determinant. Is the pump theoretically capable of moving water? The Gaussian elimination. Which valves are limiting flow where pressure drops, and what happens if one fails? It's kind of funny. Implement a 3x3. So kind of wonder like what we did here. So this was this is a 3x3. So basically it did this for us. So we cheated. But I think I'm going to cheat a little bit with the help of AI, just because my limited time that I have in a day, a lunch break, to really study this stuff. And thank you, AI, for being able to crank some of these lessons out very fast and efficiently. And I know I'm cheating a little bit, but that's okay. This would be really neat in computer science, more advanced algorithms and math course. Maybe if I could do the college all over again, hey, I could have studied that. All right, so maybe we can even cheat a little bit and then look a little bit at 5 determinants and Cramer's rule. Understand how early Model 3 tutorials solve regressions. Cramer's rule solves linear systems using determinant. It works well. Learning what scales poorly. Replace columns x transpose x with x transpose y and divide determinants. This explains why earlier code tutorials work. This is in the Java form. This is actually living in the program object. Compute determinants by hand. What happens when determinants are approximately 0? Why does noise break Cramer's rule? Implement determinant. All right, I'm gonna just try this. Do a little bit more cheating. On day 5. Wonder if we can even add that to here. Can you add that to this script. Just kind of curious to even look at some of this. All right, so yes, this is a perfect day 5 bridge. So I might even look into the vibe coder repo, because I know this code lives exactly in Java land. So if we look through here, lots of Java, lots of data structures. I do think it's kind of important to kind of study the code that AI pumps out, where if it has to troubleshoot something, that you can kind of zero in on it if something isn't working right. Sometimes at night I like to look at this code like offline of the computer, maybe like on Amazon Kindle or something like that. I like to just kind of scroll down. This, I think we'll get into this. No, wait, this is model. That's model 1. Model 2. Model 3. Fit once. That's where our matrix algebra lives. So I think this is kind of like what we're getting into a little bit here. Except this would be more geared towards the PNNL equation. So this is what we're doing under the hood in Model 3. And then like this function here, we return the determinant. Same thing as here. So Python world right here, compute the determinant, and then in Java we're doing it. Looks really similar. Copy our code. Run our Python script. Python is like just so much easier to look at than Java, and you don't have to compile it. Compiles at runtime. Oof, actually, try that. So then, what would it be? I think we're missing something. Determinant is 8. Quite a bit of math going on there, so it's like adding up these values. There's adding, multiplying, adding, then subtracting, then subtracting, then subtracting, you know, kind of cool. What is going on there? How this fits into Model 5, Day 4, which we did first, this is how systems are actually solved. Day 5 scalar determinant tells us if we're allowed to solve. Cool. I think it's helped me. So thank you for following along. We're just kind of looking at this stuff at a really high level. And maybe as the days go on, I can show you how the program objects are working in the field. I just find it so much easier to look at coding. Like if I had to take a math class these days, like I remember in college 20 years ago, in early 2000s would be like be like, where's the code? Where's the coding language? I'd have a hard time doing it all by hand again, but I probably could if I had to. So that's all I have, guys. I think we'll just stop for today. I'm very thankful for artificial intelligence at kind of assisting with us. So until tomorrow, have a great day today.